Okay, excellent. Yeah, so welcome everyone to the seventh season of the Isogeny Club. And for the first talk this season, we have Bruno again. As you might know, you long-time Isogeny Club members might remember that he also gave a talk in season one. But now one looks kind of like a seven if you draw it a bit sloppy, so it makes sense. And yeah, he's a postdoc at in Paris, and he will, well, for at least a few more days or so, and he will give us his talk on finding large smooth twins. So please take it away, Bruno.
Thank you so much for the introduction and the re-invitation to have me back here. Um, it feels like yesterday when I gave the talk here, but that was like many, many years ago. But anyway, I'm happy to be back. So today I want to talk about this very, very recent work that we put on ePrint in collaboration with these Dutch guys, Erik and Wessel. And the idea is we want to find certain type of consecutive integers. In particular, we want to find these integers here that are highlighted in purple in comparison to all these others integers that are highlighted in gray. Now, you might be wondering why we were interested, and you could probably think of a million reasons, or maybe a lot of reasons, why these numbers that are in purple are particularly interesting. One very natural reason is when you look at their factorization. Now, for integers of this size, what do you expect from their factorization? Well, you should expect there to be some kind of a large factor, large prime factor at least. I mean, this first integer ends in 1 has this really big prime factor. Some of them are a product of large primes. Occasionally you might find primes. There's not one here, but there might be a prime in this list of consecutive integers. Some of these integers have small prime factors, like there's few that have prime factor 2, which occur more frequently, and maybe a prime factor 3. But generally speaking, for integers of this size, you should expect there to be a large prime factor. Now, in these ones in purple, it's the exact opposite. These are what we call smooth integers, and the largest prime factor is very, very small. I mean, the largest prime factor in both of them is 200. And it's even more rare that they are next to each other. And we call such a pair of consecutive smooth integers a smooth twin. These smooth twins have appeared in the Isogeny Club before, back in season 2, when Michael Meyer talked about them and gave a few algorithms for finding them. And my talk is pretty much going to be to try and find these pairs of consecutive integers with this new algorithm that we propose. So why are we interested in these type of consecutive integers? Well, they have appeared in the context of isogeny-based crypto. That's why we're all here. And what we want for isogeny-based cryptography is we want large primes of cryptographic size, I'm going to call them P, such that P squared minus 1 is either smooth or has a large smooth factor. So it looks somewhat similar to this consecutive smooth integer thing, which I will show how they relate to each other in a second. But these sort of primes appear in certain types of crypto systems. It first appeared in this B side, which is a key exchange adapted from SIDH with smaller keys, which no longer exist because of these SIDH attacks. But there's a few other things. There's the first version of SkiSign, and there's some ideas of doing this with Pocket, a new isogeny-based encryption scheme, but might need updating, might need rethinking, but could be used in that context. And the idea is you're working with elliptic curves that are super singular, and either the number of points on their curve is p plus 1 all squared, or it's p minus 1 squared. And you can translate between these two by working over the quadratic twist. If you apply the quadratic twist on E over FP squared, you get start from, let's say, an elliptic curve with p plus 1 all square points, and you translate that to one with p minus squared points. And I've given this type of talk a few times, and I like to showcase this little meme that I kind of came up with. And it's finding these sort of primes is some kind of meet in the middle, whereby the meat is the middle of a sandwich, and it's sandwiched between two smooth pieces of bread. Anyway, yeah. Relating this to smooth twins, if you have a smooth twin and you add these integers together, so you get p equals 2r plus 1, if this is prime, then you get a prime that you want for cryptographic applications. So this p squared minus 1 factors exactly as r times r plus 1 up to this factor of 4. And I should say that I might call these sort of primes here smooth sandwiches for this reason that I had in the meme. Now, in isogeny-based crypto, you don't necessarily need all of p squared minus 1 to be smooth. Sometimes it's sufficient to just have a large enough factor. And I'll showcase this in practice through SkiSum 1D and the results that we've come up with in a few slides. Now, finding these smooth twins, this is a really, really hard problem. And it's really, really challenging if you want to keep the smoothest bounds really, really small. If you don't care too much about the smoothness bound, then you can find them, but they will be quite large. But to like optimize the efficiency of isogeny-based instantiations, you want to find them with as small a smoothness bound as possible. So that's like the main problem that we're going to focus on. But I want to showcase like these cryptographic applications. So I want to showcase this SkiSum 1D application. But SkiSum as a general thing is now what I think at least is a family of isogeny-based signatures based on the Fisher-Shamir paradigm and the Düring correspondence and supersingular elliptic curves. And the idea in all the variants that we have right now is as follows. We have some public elliptic curve, and we want to prove that we know its endomorphism ring, or equivalently, the isogeny that connects it to this special curve E0. And we construct an identification protocol. So we do a commitment and a challenge. And the response is going to be some representation of an isogeny between this public curve EA and this curve E2. One isogeny that we can give is just a composition of these three, but that's kind of stupid because that just gives away the secret that we want. And really what you would need to use is the fact that you know the endomorphism rings to compute a new isogeny between EA and E2, and a new one-dimensional isogeny for which you can efficiently evaluate and verify that this is actually an isogeny between EA and E2. Now, the differences in the variance is how you represent this one-dimensional isogeny. In the original variant, which is the one I'm going to be focusing on in the next couple of slides, we represent this as a smooth degree isogeny, or more precisely, an isogeny of degree some power 2. This, with the algorithms that we have right now, this isogeny is quite long. We would prefer to have it shorter, but like the algorithms really like can't make it smaller in any way. The advent of these HD variants shorten this chain. Firstly, it was the idea of verifying with 4-dimensional isogeny. So this is two isogenies. And then more recently, we can verify this isogeny with 2-dimensional isogenies. And this latest version is far better than either of these two variants. But I want to revisit SkiSum 1D for my purpose of finding smooth twins. So SkiSum 1D parameters, they look like this. We want a prime for which we have some large smooth factor of p squared minus 1. It includes some large power of 2. And some odd smooth factor I'm going to call t of size, let's say p to the 5 over 4. What all of this is going on, like in the signing, what's going on is really you're computing a lot of T isogenies, and actually the number of T isogenies that you compute is somewhat inversely proportional to the F that you have. So the larger this F is, the less T isogenies you have to compute. But at the same time, if you're going to have a larger F, then all of T squared minus 1 needs to be smooth, and that makes it really hard to find these parameters, and it really makes it annoying. The verification is really, really easy, because what you just do is just compute a chain of 2 isogenies, or a chain of 2 to the F isogenies, because that's how much accessible 2 torsion you have. And obviously, everything is more efficient when you have a larger F. Now, finding Ski-Sign 1D parameters, like the general idea is to do some kind of boosting strategy. This was mentioned in Michael's talk back in season 2, but I want to give like a brief high-level overview. The idea is we're going to use this polynomial 2x squared minus 1, and we're going to evaluate this at some well-chosen integer r that has a large power of 2 in there. And this ensures that we do actually have a large power 2 in p plus 1. Actually, it's amplified by the fact that we have this square in the polynomial. And actually, the power of 2 we have is 2a plus 1, which is nice. And we choose this r in such a way that we have all of p plus 1 smooth, but also enough factors in p minus 1. And a small remark that that you should like not remember, but at least like think that there's something like this that exists, is that if the power of 2 is something like log p over 4, then the combined smooth factor in p squared minus 1 is at most the size p to the 3 over 2. In the latest Ski-Sign primes, the power of 2 is roughly this. So it's worth having in mind. So how do we instantiate in terms of finding this R? The first idea that I'm going to briefly overview is the boosting with a sieve. And the idea is we're going to basically exhaust all of R, but in maybe a little bit more specific way, whereby, I mean, if you exhausted all of R, it's going to be impossibly vast to just search over. But if we include some large power of 3 in the M, we can shorten down this search. And actually, this power of 3 will help us in the signing. So we do some kind of sieve of Eratosthenes to identify smooth integers, let's say M prime in a large enough interval. And then we evaluate it in the polynomial and see if it gives us a prime and all the factors are smooth. This was done when the NIST submission crew for Ski-Sign first submitted it to the NIST proposal, and they chose this prime to give 256-bit security, 128-bit security. Yeah. The other way we can find these sort of primes is with an actual smooth twin. And the observation that we should make is, for such a prime P, we can compute the factorization of p squared minus 1 and see that it is now 4r squared, r minus 1 times r plus 1. And if we have a smooth twin, let's say r and r plus 1, then we automatically get a large amount of smoothness in p squared minus 1. In particular, we get this p to the 3 over 2. And this 3 over 2 is probably what you remember from a few slides before, is kind of the size that we want. So this means that like all we need to do is find a smooth twin. If it has a large enough power of 2, and let's say if it's less than log p over 4, then all we need to do is check that it's prime. And if it's larger than log p over 4, then we might have to see if there's some other factors in r minus 1 to give us enough smooth factors for t. But the chances of this happening is actually quite large. So this is an okay sacrifice to have, as long as f is not too large. Now, instantiating this smooth twin oracle is really, really difficult. So in this context, you really want to find, let's say, 128-bit smooth twins with a very, very small smoothness bound. That's very, very challenging. And with all the algorithms that we had before, it's very, very not very easy to instantiate those properly. In the talk that Michael gave, he actually presented a prime whereby instead of working with P2x, he worked with this P4x, whereby we replaced the power of x from 2 to 4. And you use the CHM algorithm to find a smooth twin and evaluate this polynomial to get a ski-sign prime. And this prime is not as good compared to the previous one for a whole bunch of reasons, but like the big standout one is like the power of 2 is really, really small. And the signing is just not as efficient compared to the previous one. But in this work, we can instantiate this oracle. And I want to showcase just this 246-bit prime, whereby we have a really large power of 2, and the largest prime factor in all of p squared minus 1 is 500. Much, much smaller than, let's say, the NIST prime, which was closer to 2000. But it still gives us a faster signing. Now, I say faster signing compared to the NIST ski-sign 1D, it's not going to compete with all the 2D variants. So this here, I'm just presenting this as like, here we have something cool. So now I want to talk about how I actually found this smooth twin. To just formalize things a little bit, when I say a smooth twin, I might sometimes call them B-smooth twins, whereby I'm specifying the smoothness bound of our pair of consecutive integers. So I call R and R plus 1 B-smooth twin if, let's say, the product is B-smooth. I have these two examples that I always showcase to everyone. These are like my favorite for a whole bunch of reasons, which I can go into at the end of the talk if you guys want to know. But I always like to showcase these ones. An interesting fact is that back in the 19th century, Schnorr proved that this set of B-smooth twins is finite. So you can't necessarily find, let's say, smooth twins of cryptographic size with a smoothness bound like as small as, let's say, 3 or 5 or something. The smoothness bound really has to grow as you want to increase the size of the smooth twins. For instance, this 7 smooth twin that I have up here, this is the largest 7 smooth twin among all 23 that there are. This 23 smooth twin, I think there's one that's larger, but it's still pretty large. And I will call some smooth twins optimal. And by optimal, I just mean the largest one, the largest smooth twin among the set of B smooth twins. And in the other direction, I might call B the optimal smoothness bound in that context, but I might not use that all the time, but I will refer to some smooth twins as being optimal. Now, in terms of finding optimal smooth twins, there's only really one method in the literature that we have, and that's by solving Pilot equations. So for some notation, I'm just going to write PB to be all the primes up to B, and usual notation, pi B to be the number of primes up to B. Smooth twins can be seen as a solution to some kind of Pell equation. The idea is the x that you construct from the smooth twin is the sum, a bit like what I had for the cryptographic application. So x is 2r plus 1. Then when you factor x squared minus 1, you see that it's all B smooth, and you decompose it into its square free and square part, and you rearrange it and you get a Pell equation like this. So you can reverse this and find all B smooth twins by solving all of these Pell equations. This 2 to the pi b comes from the fact that you have that many combinations of possible square-free smooth integers that you can choose. So for instance, with b equals 7, we have all of these Pell equations that we have to solve, going from C2 all the way up to C to 10. Off the top of my head, I think the seven smooth twin that I had on the previous slide comes from this solution, I think. Now this has been implemented for larger B. First, Lamer implemented this for B equals 40, and then subsequent work have done it for larger B. We found out recently that Costello's implementation with B equals 113 is a little bit heuristic, but there's some newer work that improves on Luca and Nyman's work and actually does this computation provably for B equals 113. So this is us finding all B smooth twins. What if you're just interested in finding the optimal one? Well, really, you don't have an advantage. You really don't know which of these Pell equations you have to solve in order to find this largest B smooth twin. It's not like I know it's here or I know it's there. And this is where I introduce my new kind of categorization. And at a high level, the idea is smooth twins arise as short vectors or particularly short vectors in a certain type of lattice, which I'm going to call the prime number lattice throughout the rest of this talk. And in particular, the shortest vectors in the lattice correspond to pairs of integers, which are smooth, they are coprime, and their difference is small. Might not necessarily be one, but if you choose your parameters correctly, then you can make them quite small, even one. And as I said, you can parameterize the lattice in such a way that you really target finding the largest B-smooth twin. For instance, what I'll showcase later on is that we found this 751 smooth twin of 196 bits, which we believe to be optimal, is the largest among the sets of 751 smooth twins. This is not the largest smooth twin that we found in this work. We did find some larger ones, but they're not optimal. We can give some evidence to suggest that there might be some larger. Also, we find some new smaller twins that were not known before. And in particular, we conjecture to have the complete sets of 200 smooth twins, of which has this many. There are this many of them, which would improve the previous known result if we can actually prove it. Okay, so I've talked about my idea being based on lattices. So let's just give like a few slides to set the foundations of lattices, not necessarily because you don't know it, but just to set the notation. So a lattice, in a very abstract sense, is a discrete subgroup of R to the n. And when I say R to the n in this case, I really mean R to the n equipped with the Euclidean norm, one that you would use on a regular basis. Equivalently, we can say that a lattice is an integer span of linearly independent vectors. Written in this way, whereby these are the linearly independent vectors, or we can group them together in the form of a basis. Not basis, in terms of a matrix. Now, short vectors in this lattice are vectors that are non-zero and have a small norm. And the shortest vector problem is the one that asks the shortest vector, so that minimizes this norm. And I'll often write the actual norm of the vector like this. This lambda 1 stands for like the first minima of the lattice. Now the Gaussian heuristic gives a somewhat expectation on what we can expect this first minima to be on average for lattices. And on average, we expect it to satisfy this, whereby I'm saying this is like the Gaussian heuristic. And also, the Gaussian heuristic says that the number of vectors of norm less than, let's say, some lambda is this. In some sense, this is exactly the same as you intersecting the lattice points with a ball of radius lambda, and this is the number of vectors in that ball. That's also lattice points. Now, if you choose a specific lattice, it might not necessarily be the case that it follows this Gaussian heuristic. But if you choose a random lattice, and by random, I'm not really going to talk about it too much, but I just want to say it here. Choosing a random lattice, this heuristic should hold. And this is something that would be relevant if we were doing lattice-based cryptography. And the lattice that I'm going to showcase to you later in the context of our smooth twins is not a random lattice at all. But we're going to model it as if it did abide by this Gaussian heuristic. And in most cases, it does. There are a few exceptions to this, but I'm just going to, for the sake of this talk, model it under the Gaussian heuristic. So now we want to see if we can actually find short vectors, or more precisely, we want to solve SVP. In a previous episode of the Isogeny Club, we got introduced to lattice reduction, LLL and BKZ. These algorithms can find short vectors, but they might not necessarily find the shortest, especially if you're working over a lattice in large dimension. So what algorithms are there to find the actual shortest vector? Well, there are two. There's lattice enumeration and lattice sieving. I'm going to highlight lattice sieving on this slide. So lattice sieving is an algorithm that's it's an iterative algorithm. In each iteration, what you do is you have a large list of non-zero vectors and a large list of this size, roughly speaking, and whose maximal norm I'm going to write as Ri. And in the next set, you're going to construct another set of vectors whereby you take all pairs of differences of the vectors in Li that are different, and also their norm is less than this Ri that we had before. Now this new list will have roughly the same size as this n that we had before, basically because the probability that two vectors have a norm difference that is less than r. If you hold on, let me say that again. If you want to, so there are n squared pairs of lattice points, roughly speaking, or on the order of, and there's a probability attached to the fact that the difference norm is less than Ri. And if you want to have the same number of vectors as you had before, and you solve the equation, then this is what you get from that. And you repeat this until you've saturated all shortest vectors of norm less than this, square root 4 divided by 3 times the Gaussian heuristic. And as I said, this gives all the shortest vectors, including including the shortest that you want to solve for SVP. Now, there's ways that this is a very naive lattice sieving. There's some ways to improve on this. And the state of the art is to use buckets. So you'll sort your vectors into certain buckets, and you only test their difference if the two vectors lie in the same buckets. And with high chance, then you won't miss out any vectors that you might have missed if you would have done the full thing. And you save a little bit there. You also save a little bit by carefully choosing your buckets, and you can do this by using coding theory, which I'm not going to talk about at all here. But the runtime of like the state of the art in terms of doing lattice sieving is 2 to the 0.292 times k, and there's some memory attached to this, which is a little bit smaller. All of this is implemented in Jessica, the general kernel sieve. It's a general sieve kernel. And it is written like this, and this actually stands for Jessica. Jessica. Anyway. So let's talk about the lattice that we want to that we want to work with. Again, we're going to set up some notation. We're going to fix some set of primes P that is less than B, let's say ordered in terms of increasing size. The number of primes in this set is, let's call it n, and we have some real numbers alpha and alpha I. Often I'll call this set of primes P a factor base. And I might sometimes call the, oh, Jesus Christ. And I might call the weights alpha I, or the alpha I weights. So I've sneaked ahead with the slide, so you might have seen this lattice. So this is the lattice that we're going to be working with. And it's generated by this matrix. Now, this lattice might be something that you recognize before, might have seen this lattice before. If you're familiar with the integer factoring literature and the computing discrete logarithms literature, then you might have seen this in that context. Schnorr, back in the 1990s, proposed factoring with this lattice, and also computing discrete logarithms with this lattice. And there's been some others working on this. Adelman, I can't speak. Other people have worked on this lattice. But unfortunately, in terms of factoring integers or computing discrete logs, this doesn't compete with other algorithms that exist. For instance, like the number field sieve or something else. But we're going to use this in our context. But firstly, before we do this, I want to showcase what the lattice vectors actually look like. So if I have some x, the lattice vector in this lattice looks like this, whereby the first column is this integer sum of alpha xi times log pi, and the other entries is just a diagonal identity matrix almost. So it's just going to be the weights alpha I times xi. Now we can combine this big sum into one term, whereby we use the law of logs to get them all together. And really, I mean a divided by b in terms of like the exponents pi and the xi's and the primes pi. And you really do get a division here because some of these exponents could be negative. And also this a and b are co-prime, essentially because you just have, let's say, you either have x1 being, let's say, positive or negative, and so that affects whether it goes into A or B. Now, equivalently, we can go the other way. We can start with the smooth rationals and compute what the xi's are going to be in this way. Essentially, from this factorization, we can compute what the xi's are. So we have this kind of correspondence between p smooth rationals and lattice vectors in this prime number lattice. Now, I've hinted that we want to find short vectors in this lattice. So what do they look like? Well, firstly, I should note that the square norm of vectors in this lattice looks like this. We take the square of this first term, and we have a sum of these squares from the weights. Now, this first term is the crucial term when looking at lattice vectors. And you might observe that smooth rationals that are fairly close to 1 give essentially a 0 contribution over here. It's technically speaking true because you have to account for this alpha. But that essentially tells us that like this is the most important thing. And I want to showcase why that's the most important thing with a few examples to visualize what the actual short vectors look like. We're going to start first with small alpha, and we're going to work with the prime number lattice with a factor base, all the primes up to 7, and the weights being log pi. I'm going to talk about the weights in a second, but I'm just going to fix that on the get-go in this slide and the next few slides. And we're going to compute or like list out what are the shortest vectors in this lattice. And when you do this for small alpha, let's say alpha equals 2 to the 8, 256, then these are the short vectors. The first vector is this one, and it corresponds to a smooth rational. And also, these things differ by 1, so you get a smooth twin from that. And you notice that most of the short vectors here correspond to smooth twins. There are some exceptions, like this one, that differ by 2. And they're both odd, so you can't divide it by 2. And then there's this one as well. If we work with the same lattice, but we increase the size of alpha, before we had a 256, and now let's change it to 2 to the 13, 8192, then these are the shortest vectors. You see that the first two, they correspond to smooth twins, but after that, they definitely do not correspond to smooth twins. And I should have said in the previous slide, let me do that quickly while I remember. These shortest vectors in this lattice, the A and the B, they somewhat correspond to the size of the alpha that we have up here. The alpha here is 256, and that's roughly the same as over here. And here we have roughly the same over here. Okay, here there's a bit more of a larger gap between 2,400 and 8,192, but it's more or less the same, maybe up to some small factor. Now let's do the same thing, but for even larger alpha. Now, if I choose alpha to be 2 to the 18, you now see that the shortest vectors correspond to smooth rationals that definitely do not give smooth twins. They have a much larger difference. And it's not like the smooth twins that we had before are not in this lattice, because I told you that there's this correspondence. So they are in this lattice, but it's just no longer short. The factor between the shortest and this one is much larger. So you really can't find it from the shortest factor. Now let's do the same thing, but we increase the factor base from being all the primes up to 7 to all the primes up to 19. And let's do the same thing as before with the same alpha. So alpha is 2 to the 18. And now you see all the shortest vectors in this lattice correspond to smooth twins. One exception here, like we had with the small alpha before, but they more or less correspond to smooth twins. And again, you should note that like this integer here, roughly speaking, corresponds to this alpha that we have up here. So with this visualization in mind, we see that like really alpha dominates the control of short vectors in this lattice and really correspond to these smooth rationals that are very close to 1. As I kind of hinted before, the shortest vectors have an alpha that's roughly this, and if their difference is 1, then alpha is like pretty much the same as A. Or B, because they do differ by 1, but whatever. But this is a bit vague, and we can be much more precise about this and do a straightforward calculus exercise to see what the best choice of alpha is to kind of minimize the shortness of the corresponding vector in the lattice. And the optimal alpha that you get is this. And you can see that it's a little bit more than the A divided by A minus B that we had before, up to this like small factor here. This beta 2 is determined by the exponents in this smooth rational. And you might think, okay, if I want to use this to like compute the alpha beforehand, then I must know what the factorizations are. So a priori, this is not particularly helpful. But we don't have to be so precise. If we, let's say, choose a slightly smaller b, then the contribution from this term doesn't really change so much and really doesn't drastically change how much shorter it's going to be. I mean, okay, if you increase it, then it might have a larger contribution because this will kind of grow much more. But if you just approximate it to be something maybe a little bit smaller than this, then you're fine, and it will be a short vector, and you can find it with lattice sieving. So we've talked about the alpha. Now let's talk about the weights and actually getting some theoretical and experimental results on actually the shortness of these vectors. There's various choices that are in the literature and some that we came up with. In the literature, the first choice that was noted is this log pi one that I had in the previous slide. Some newer versions of the prime number lattice choose the weights to be square root log pi. But you can choose other weights as you want. And choosing this weights kind of influences how your exponents are going to look like. If you choose alpha I equals 1, then basically what you're saying is all the vectors, all the exponents are pretty much going to be the same. It's not like I'm going to have a favorable choice of a large power of 2 versus a large power of 113, let's say. Versus if you choose, let's say, a weight to be, let's say, log pi, then you're maybe influencing a maybe slightly larger power of 2 to be a short vector in this lattice. I'll go into some of this a little bit more later on as well. What we do in our paper is with a choice of weights alpha I equals log pi, then we show under some heuristics that optimal smooth twins and choosing the optimal alpha correspond to a particularly short vector in this lattice. And occasionally it might be even the shortest vector in this lattice. Not always, but most likely, or fairly likely to be the shortest. Now for different exponents, we didn't manage to get provable results on the heuristics, like for this one, but we experimentally showed that like for optimal twins, these vectors are also pretty short, at least the vectors corresponding to optimal twins. Now, for non-optimal twins, for like these smaller ones, some might correspond to the shortest vector, as we saw in some of the previous slides, but not all of them. And there's kind of two main reasons why. Firstly, there's much more smaller smooth twins than there are larger twins. So it's natural to think that some might have a larger shortest vector or might not be as short compared to others. But more precisely, some might have a larger exponent on the, let's say, pi, which gives a larger contribution coming from this particular weight. And that means that like that's particularly it's not expected to be that large, and so that contributes to the norm. The example that we have in this paper is this smooth twin R equals 107 to the 6 minus 1. And clearly you can see just from looking at it that R plus 1 has a large power of 107, which is really unusual and contributes to a much, much larger norm compared to other vectors. Okay, so hopefully I've convinced you that smooth twins, optimal smooth twins correspond to short vectors. Now let's actually go into like finding these smooth twins. So the simple strategy is as follows. We want to find B smooth twins. So we set up our prime number lattice. We make some approximate choice on the alpha that we want. We choose weights we choose whatever weights we want. And now we work with this lattice and we find short vectors in this lattice using lattice sieving. And for each vector that you get from this lattice sieving step, you're going to compute the smooth rational that you get corresponding to that vector. Or like plainly speaking, compute the numerator, which is this A, and this denominator, which is B. And then you present all the pairs that differ by one or actually give smooth twins. Now, there's a really nice small remark that I want to mention. For those that know the CHM algorithm, which I hinted at before, there's a really nice similarity between the lattice sieving step and CHM algorithm in the sense that the underlying operation that you do in both of these steps are exactly the same. up to, let's say, there's a additive versus multiplicative difference between the two. In lattice sieving, you're taking differences of vectors, and in CHM, you're doing some kind of multiplication and division. I'm not going to talk about it too much, but they are fundamentally the same. The difference between these two algorithms is how they go about finding smooth twins. In the lattice sieving algorithm, what you actually do is you find large pairs. You start with large pairs that really do not differ by something small. They're really far apart. And then in each iteration, you try and make them smaller and smaller and smaller. Whereas in CHM, you start with really, really small smooth twins, and then you constructively produce larger and larger smooth twins with this operation that we do. Okay, let's actually present some stuff. Before I present the optimal smooth twins that we found in this work, I want to talk about the previous known results for B less than 113. And the largest smooth twin that we have in this setting is this one. And as I hinted at before, this required solving a lot of Pell equations at exponential cost in terms of the number of primes that you're working with, which means that working with B equals 113 is the largest you can feasibly work with. Now we're going to do our lattice sieving approach. So we find short vectors in this lattice for some large enough alpha. And let's say we want to find this 103 smooth example. What we might do is choose alpha equals 2 to the 76. So use lattice sieving to solve SVP and actually get this, you would get this, this smooth twin. And now that we know the smooth twin, we can compute what the optimal alpha is, and we can see that it is fairly, fairly close to what we estimated it to be, at least when we chose alpha I to be log pi. Now this is very, very easy to do. It probably takes less than a millisecond to run the code. Okay, that's maybe a bit of an exaggeration, but it's very, very quick to run this. So we can do this for larger B. If we take B equals 200 and choose this alpha to be 2 to the 97, then we get this smooth twin that I mentioned on the very, very first slide. Yeah, which is very, very cool. And the reason why this is very, very easy to find is that we get a saving in the computational cost, the complexity. So we reduce down the complexity from 2 to the pi b to 2 to the some constant times pi of b, where this constant comes from the runtime of lattice sieving. Now, this was very, very easy to do, so we can do this for much larger b. For b equals 500, you can choose this alpha to be 2 to the 160 and get this smooth twin. And then choose b equals 751 and alpha equals 2 to the 198 and get this smooth twin that I mentioned before. Now, all of these twins that I mentioned here that are greater than, whose smoothest bound is greater than 200, the optimality of these twins is a bit conjectured, but we give strong evidence based on the heuristics that are in the paper that these are optimal. Now, hinted also that we found some larger twins, which are not optimal. And you can do this by introducing some trade-offs in the lattice. There's two things you can do. Either you can incorporate this dimensions for free trick, which is a trick from Leo Ducat, published at Eurocrypt in 2018, whereby you take the lattice and you project it down to some lattice of smaller dimension, solve SVP there, and then lift the vectors back up to your original lattice. So that's the lifting technique. And then there's guessing. You can reduce the size of your dimension by guessing what prime factors are not going to appear in your smooth twin. So you start with your PB and you remove some primes that you hope are not in there, and you sieve in that lattice. Now, if you combine enough lifting and enough guessing with B equals 100, then you can find this 213-bit smooth twin. Now, this is definitely not optimal. In our paper, we use our heuristics and estimate what the largest 100 smooth twin should be, and there's a bit of a gap between the 213 and the 227. So a few remarks before I conclude. At the start of this project, it would have been really, really cool if we can apply our lattice technique to get 256-bit smooth twins. Unfortunately, there's like a limit coming from the lattice sieving. We've gotten really, really close, but not quite 256-bit smooth twins. Now, these should exist with our heuristics with B equals 1250. But if you wanted to do it, you'd have to incorporate an awful lot of guessing and an awful lot of lifting. And if you do this, then you really decrease the chance that you actually find short vectors that correspond to smooth twins. So these smooth twins are out of scope for us. I want to talk a bit about this ski sign twin that I mentioned at the start. For that application, we wanted the large power of 2. And I hinted that maybe a large power of 2 would give a larger contribution to the norm compared to, let's say, other vectors. So let's see. There are 2 tricks that we can do to help that compensation. Either we can replace the prime 2 in the factor base with a larger power of 2. And what this does is the vectors that you'll get are correspond to smooth rationals whose power of 2 is a whose exponent of 2 is a multiple of a. So it might be that r and r plus 1 have a factor 2 to the a, or 2 to the 2a, or 2 to the 3a, or so on. This is a little bit restrictive because you have to essentially do your lattice sieving with a particular choice of power of 2. And maybe, and I think a slightly better idea is to modify the weights. Now you can modify the weights so that, let's say, with the first entry, alpha 1, you decrease that by some factor. Instead of having it being log p1, you change it to be log p1 divided by some eta, let's say. And you keep all the other alpha i's the same. And what this does is decreases the contribution of that weight in the norm. And for instance, this smooth twin that was in the prime that I mentioned at the start, if you choose eta equals 5, you can easily find it with by sieving in the full lattice, with a factor base being all the primes up to 500. Which, if you didn't make this choice, you wouldn't be able to do it in the full lattice. You'd have to incorporate some guessing or maybe some lifting in order to find it. And then I also mentioned that like we had this conjecture on 200 smooth twins. Now, this conjecture, finding all these smooth twins with just the lattice approach is kind of bad. It's worse from a practical complexity perspective compared to, let's say, doing it by solving Pell equations. But what we do is we start with a really large set of B-smooth twins that are already known. For instance, we took the smooth twins that were found in the CHM algorithm, and then use our lattice sieving techniques to find new twins on top of that. And for the smooth twins with a smoothness bound less than 200, we got to a point whereby we found a lot, or found a few more, and for like weeks we couldn't find any more. Maybe even like months we couldn't find more. So I was very happy to like state this as a conjecture. For larger B, I'm not confident to make that conjecture just yet. So to wrap things up, we found new smooth twins from the prime number lattice. And in particular, we've improved the literature on the largest B-smooth twin. Before, this was only known for B less than 113, and the largest in that case was 75 bits. And we've increased that dramatically by finding this 751 smooth twin that's 196 bits. I also said that we found some larger ones, but those ones are not optimal. And then also, yeah, I mentioned at the end that we could apply our algorithm to get some new parameters for isogeny-based constructions. I think my time is up, so let's see if there are any questions.
Thank you very much for the talk, Bruno. As always, if you have any questions, please just unmute or type them in the chat.
Oh, sorry.
Okay, I will ask the question. What is the next slide?
Ah! Right, okay, I will showcase this. So there were two smooth twins that I said were my favorite. The 7 smooth twin is one of my favorites because of the CHM algorithm, which I'm not going to talk about. The other smooth twin, which is my favorite, this is the reason why it's my favorite. So we're living in a magical year. It's 2025. It's a square year. How exciting is that? And it's 45 squared, but 45 has some factors, and we can factorize it as 3 squared times 5. And so 45 squared, 2025 is a smooth number. Last year was 2024, even more exciting year to be alive, because it's a difference of 2 squares. It's 45 squared minus 1 squared. And this we can factorize as some smaller factors. We have the factors of this being 8 times 11 times 23. The year before that was 2023. And a priori, 45 squared minus 2 shouldn't have small prime factors, but this one it does. It's 7 times 17 squared. So now I have a bit of a dilemma, right? How do I choose my favorite smooth twin? Is it 2023, 2034, or 2024, 2025? I have a choice here. But I can do something better. I can take this triple of consecutive smooth integers and turn it into a large smooth twin, which is the one that I had before. And I think this has to be my favorite, especially because I've been working on smooth twins in these years.
That is quite amazing, actually. Very cool. I also want to comment that your name Sterner is phonetically extremely similar to Sturmer.
I
Have you any thought?
hadn't thought of that before, actually. Yeah, no, that's right. That is right. Maybe we can play a distinguishing game whether I pronounce Sterner or Stormer. Okay, so I see Pierre's got a question in your chat. How does your ski sign prime compare to the best that we can obtain from the state-of-the-art techniques? Could you go higher security levels than P499? Two parts to that question. The comparison between this prime and the one that is in the NIST. Theoretically, you should be able to get a faster signing. This is theoretical because in practice, you probably have to consider a few things on the implementation side. Verification will be slightly slower because it's not quite as large a power too, but that's a negligible cost to have it being a little bit slower. So I think it's competitive in that sense. Now, talking about the higher security levels, now you can instantiate the boot twin and boost method for larger twins. And if I was able to find enough 192-bit smooth twins in order to essentially instantiate the oracle of doing the boosting method and then getting having enough smooth twins to get a suitable prime for the ski sign application, then I could have. It's just that it was just not quite good enough. So I think at the moment I will struggle to get primes for large enough security. Wessel says we didn't have the GPUs for that. Yes and no, I don't think. I think because you did run some stuff for that level. but maybe we didn't target specifically having a large power 2. And maybe if we incorporated this factor eta, choosing that to be less, then maybe we could find something for larger security levels. And I think if you were to do this, you would probably be able to significantly improve the signing performance at, let's say, that level compared to what we have right now. Because right now for NIST Security 3 and SkiSign 1D, that's rather slow because you have to have a really, really large smoothness bound. Whereas if you did the twin and boost thing and got 192-bit smooth twin and have the smoothness bound being really, really small, then you could be able to boost that and have a really, really small smoothness bound on p squared minus 1 and use that for your thing. Yes, indeed, SkiSign 1D level 3 to 5 performs poorly. Yeah, I mean, that's the main problem with SkiSign 1D. The scaling is like really, really bad. Theoretically, you could do so much better, but finding them is just very, very difficult, either when you do sieve and boost or twin and boost. Okay, I see a question from Mark. Maybe you need to promote smooth twin primes for prime grid.
Yeah, that's more of a joke. But
that's more of a joke. Okay.
This is like a large distributed computational project for searching for different kinds of primes. So
okay,
if you...
I'll have a look at that. I haven't seen that before, but yeah, I'll have a look.
Can I ask another question in the
Yeah,
meantime?
please.
So I'm wondering if you can do lattice sieving for a norm different than the Euclidean one to control the shape of the twin smooth pair.
I don't see why not. At the same time, I don't know what advantage I would give.
So I think for some applications you need different kind of shapes. So you already mentioned like for SkiSign you need this large power of 2, but I think for Poke there are also some kind of additional requirements other than just having a large move factor.
Well, I think Poke there's a large power of 2 as well. Actually, an even larger power 2, if I remember correctly. But maybe for other applications, yeah, I'm not sure. I don't think, because you also have the weights as well. Let me get the lattice. You have all these weights, alpha 1 up to alpha n. So these you can like manipulate them. So there's lots of trade-offs you can do there. And I think you can probably do some trade-offs by working with a different norm, but I'm not sure how much that would give you. Yeah. Hopefully that's okay. Wessel's commented, you can, but the complexity of sieving in the P norm for P not equals 2 is worse. Okay, well, that's one way of answering it. At least from like a lattice sieving perspective.
Okay, thank you.
I also have a question.
Yeah, sure.
So if I am not mistaken, also in SkiSign you need this large power of 3, maybe, or like it's desirable to have a large power of 3 in Is that another thing that you explored, or maybe like analogously to how you did it with 2, would it also work if you did the same for 3?
Good question. Yeah, we did think about this, but I think the trouble there is you would probably need a larger smoothness bound, and I'm not sure if we could be able to run that. Is that true or not? No, we definitely did think about it. I mean, you couldn't choose these etas on both the prime 2 and the prime 3, so you can definitely like influence wanting a larger power of 2 and a larger power of 3. But yeah, I think you'd have to increase the smoothness bound a little bit and maybe reach a point whereby it's not quite as practical with our lattice sieving method.
Yeah.
Yeah, I would need to double check this, to be honest, because can't quite remember.
Yeah, I'm not super familiar with lattice things, but is it right to think that here the bottleneck is really like the efficiency of the algorithm rather than, I don't know, in CHM the big bottleneck was memory, but here it's efficiency?
Well, there's memory as a bottleneck here as well. The bottleneck, I think, both with CHM and this is the smoothness bound, really. If you choose a larger B, then you get a larger dimension in the lattice. And so it costs much more on the lattice sieving.
Yeah. Okay, cool.
So Wessel said we did some experiments. We did some of those experiments and it did work quite well. But indeed, as Bruno said, you force the smoothness bound to be higher, which makes the factor base and thus the lattice dimension larger. Yeah, exactly what I said. Yeah.
Okay. Are there any other questions?
I don't see any more questions in the chat, at least.
Okay, great. Well, then thank you, Bruno, again for your talk.
Thanks for inviting me again.
To have you back here. So in 2 weeks, we'll be back for our second talk of the season, and it will be given by Sebastian Spindler, who will be talking about how modular polynomials can be used to count isogenies. So hopefully see you all back here in 2 weeks.
Thank you again, Bruno.